So in the last lecture, I finally derived the number of ways you can distribute n particles in some energy levels, so that the total energy is E in some volume V, let's say. So you have some box with a volume V where you have n number of particles and the total energy is E. So this thing is a macro state. Okay? And we are counting the number of microstates. So the question was, let's say your energy has some levels. Okay. Quantum mechanically, you know what these levels are. Classically, they're just artificial. So we divide this energy into some levels, right? How do we do that? For example, if this is your energy axis, let's say, we always take a minimum size for our calculation, right? Or experiment. So what is that minimum size, dE? That will be your, let's say so that's how you count, right? 1 dE, 2 dE, and so on. So these are not energy levels, but classically we just make them levels. And so we can name them like E1, E2, E3, and so on. Let's say up to EK. Okay. So they are levels. So let's say N1 number of particles have energy, let's say E1. N2 number of particles have energy E2, and so on. They can be anything. 4 particles with this particular energy. 10 particles with some other energy, right? It just means that some particles are moving faster, some particles are moving slower, right? So we group them. We group them into, so we always have particles randomly moving around. Some will be very slow, some will be very fast. So we group them. The slower one, they're here, right? The faster one, maybe the fastest ones here. So how many of them are in which energy level, let's say? So this is the problem of assigning N1 number of particles to E1 energy level, which is equivalent to putting N1 number of balls in the first box. So these energy levels are like boxes. Imagine they're like boxes, K of them, K boxes. And then you are putting out of n number of balls, you're just choosing n1 and putting them into this first box. Then n2 in the second box. And so on, nk in the kth box. If you followed the last lectures, you will understand. So if you haven't, go back and watch them. So this is the problem, equivalent problem. Okay? How many particles have what energy is equivalent to putting n1 number of balls in the first box and so on. And these boxes, these energy levels dE, of course has some size, like, right? Let's say electron volt or micro electron volt or something. And within that, we don't consider any difference. But we can still partition them. Let's say let's say the first energy level E1 or the first box has some G1 number of partitions or cells. Let's avoid the word partition, cells inside them. But within one box, whoever is in whatever cell have the same energy. That's how we are considering it, okay? So the result of this, we did a whole class on that. The number of ways you can pick N1 and put it in first box, N2 and put it in second box, with these G1 cells, G2 cells, this whole number of ways we can do this, it's a problem of counting, it's a problem of counting, just permutations and combinations. It's now from your probability class or permutation and combinations from high school. So that comes out to be this total number of particles n factorial, product function I equal to 1 to k as many levels, gi to the power ni divided by ni factorial. This is the total number of ways you can arrange them. And so this is the number of microstates corresponding to this macrostate. And the condition of equilibrium is that this number of microstate has to be maximum. Okay? So that means the condition of maxima is always take a variation and set it equal to 0, and the condition you get is the condition of maxima. So we did that, and we have found that ni equal to gi e to the power either plus alpha, that's either minus of alpha plus beta I or plus, it doesn't matter because alpha and beta are unknown constants. So in the end you are anyway going to calculate them. If you put plus, you will find some minus value. If you put minus in the beginning, you get some positive values for them. So that's not important. So gi, alpha and beta we need to calculate. Okay, that much we did. We derived just this in yesterday's class. So what is this? It's telling us that if you follow this rule, so if you choose, like, let's say your ith box, if you choose ith box, then your energy is ei, then use this function gi into e to the power minus I beta and that ith box, energy of that box, then whatever you get from this function number, that many particle you have to put in that box. If you do that, then you will achieve the maximum value for this, and that will be equilibrium. Okay? Because we use this condition to get this. There are other distributions. You can put other number of particles, but those will not correspond to an equilibrium. Those will have less. So if you don't follow this, if you don't obey this and put different numbers, let's say this tells me I have to put 40 particles in, let's say, third box, and I didn't do that. I put just 3. Then what will happen is this will not be maximum anymore. Some less value than maximum. So you have to follow, pick your energy and use this function, get the number and put that number at that energy level. Then you get the maximum value of this. And maximum value of this corresponds to equilibrium state. Okay. Save it here again. So I probably use alpha prime and beta prime, but that's not important because we are going to calculate these numbers now. Before that, so gi e to the power minus alpha e to the power beta I epsilon I. So e to the power minus alpha is after all another constant, right? Alpha is constant, e to the power minus alpha is constant. We can just write that as constant. ECI e to the power minus beta epsilon I. So C is just this. Okay. So what are C and beta? We can use two conditions. First of all, if you added all the ni's up to k, you must get the total number of particles. So n must be equal to sum of ni, I equal to 1 to k. We can use this to find out the C in terms of n and other numbers. And then we'll use some other condition. There is another condition that your total energy will be this, NiEi, right? So N1 number have E1 energy. So for the first level you have N1 E1 energy. then N2E2, then N3E3. This way, if you sum up, you get the total energy of the whole system. This is it. This again we can use, put this here, do the sum, and we can find another constant, beta, in terms of E. So if you did this, what will you get? You will get C equal to some function of N beta, right? Everything will get summed, and in the end you will have C equal to some N from here, this side, N beta from there, so this. Then you plug it here, and this will give you your beta in terms of, let's say, some other function which will have E here and N. And finally, we'll have beta and C. Turns out that's not easy. The summations are really not easy, but integrations are easier. So this is a classical system, right? We're talking about, I didn't mention that at all actually, I should have. These gas particles are ideal gas. So they're well separated. There are lots of particles, 10 to the power 23 and more, but they're well separated so that they don't interact with each other. You can treat them like individual balls that only interact when they collide with each other and collide with the wall. Elastically collide with the wall. Do not lose any energy when they collide with the wall. Okay? Strong walls. And they're not really that fast that you have to apply special theory of relativity. So the velocities involved are much less than c. And the distance, the mean distance, let's say, is much bigger than their corresponding de Broglie wavelength. So then it will not be a quantum system anymore. And they're identical. These particles are all identical. It's not like this one is red, this one is blue, okay? This one is hydrogen, this one is some other. No, they're all identical. So yes, these are the conditions. So you get a classical ideal gas. Ideal gas. Yes, and for that, this is the distribution law. Now, you know classically that particles can have any energy, right? Their energy levels are not discrete, classically. Quantum mechanically, this is a box, and particle is inside the box. So you know how the energy levels are. They depend on the quantum number, n, and they're discrete, right? Their energy is proportional to how? N squared. Isn't it? P equal to h over lambda, right? Then energy is classic non-relativistic, so p square over 2m. So p square over 2m means h square, 2m lambda square. And what is lambda? If a particle is inside a box, its wave has to be a standing wave, right? Because any wave confined within a wall is going to be standing wave, either this or this or this. So the condition is L must be 2 lambda by n lambda by 2. N times integral multiple of half wavelength. So your lambda becomes 2L by n. So if you put it here, 4L squared, n squared. So your energy is just proportional to h squared, n squared by m, L squared. Yeah, so just look at that. H is very small number. This energy level, that it is discrete, really becomes significant, this discrete nature, when the box is tiny, like nanometer size. Okay, when you go to microscopic, so the box is really nanometer size, then only this will become a significantly, N1 will be significantly different from N2, sorry, E1, E2 and E3, this difference between them, this discrete nature becomes significant when really this number is something, like close to 1, right? But the h is really small, h is very small. So to get this number something non-negligible, you need L to be also very small. And that's why you need nanometer size, atomic sizes. So you need to take the size of hydrogen atom, let's say, as your box. But what we are talking about are cylinders, large, at least centimeter size. If you put centimeter here and mass of the gas particle and then value of h, you will see that n equal to 1, n equal to 2, n equal to 3, the difference between these energy levels are so small that you cannot even, measure them, and you will not be able to tell the difference. The size of this dE, the dE is the smallest that you have chosen to measure your energy. This difference between these levels will be even smaller than that, so you don't care. So it's like continuous. That's why classical energy looks like continuous, but they are not really. Even this chalk, if I throw, it has discrete energy levels, but it's not an observable. This discrete nature is not observable because of the size that we are talking about, because of the mass we are talking about. And that's why we can treat this problem as a continuous classical problem. Okay? In that case, what we can do is, instead of asking like n1 number of particle in the first box, so what we do is we ask instead NE number of particles in the energy range between E and some E plus dE. How many particles are there in the energy gap E and E plus dE? So we go from discrete and I's in the ith level to any number of particles in the gap E and E plus D, in the range. So that becomes, this Ni goes to this thing, and this thing will just go to integration of Ne dE. Okay, let's call this small e, because the capital E I'm using for total energy. Yeah, so this correspondence, and your Gi just goes to some G function of E dE. So this, what was the meaning of this? Number of cells within one energy level. You can think, if you consider quantum mechanics, that becomes easier to think. Like, let's say you have hydrogen atom, right? So the energy depends only on 1 over n square. For hydrogen, 13.6 electron volt by n square, right? But one energy level, let's say n equal to 2 or something, has this s orbital, p orbital. So your L values, L, M, these things can vary. But still, because they both correspond to some one n value, the energy is same. So one energy level can have different states with the same energy. So those number of states, you can treat them as Gi. Okay? Those you can. And classically, that's just our artificial division. So Gi is the GI is the number of cells in the ith box, right? But now we are going to this continuous thing. So our box becomes this range. So now what we will say, GE DE is the number of cells in the energy range E and E plus DE. So if GE DE is the number, then GE is density. So how many states are within the range DE and E plus DE? Right, is GED, then GE is density of states. Just the number of states divided by, the range where you are talking about. So that becomes your density, GE. So GI becomes GED. So GE is like density. Density times the range gives you the number. Okay. We'll use this correspondence, and then this thing will become NEDE equal to C GE e to the power minus beta E. When our energy is a continuous variable. Now things will be much easier to deal with because integration of these things are much easier really. You already actually dealt with this function during your third semester, kinetic theory, the most probable velocity, RMS velocity, average velocity. So the function was this actually. It will be very clear when I write energy in terms of momentum. So then NEDE will correspond to some NP momentum. It will become the energy range will become momentum range. But energy is a scalar. Momentum is a vector. So your DE will go to dpx, dpy, dpz. We usually denote that in this way. Or you could just explicitly write. I don't write because it takes too much space, all the time. And then the usefulness of this notation is that if there are n number of particles, you can just write D3NP. While if you keep writing like for, let's say, 10 particles, your board will be filled with dp1x, dp1y, dp1z, dp2, and so on. Okay. So this means that, and of course, your energy is this. So let me put all these things there. So NEDE is now our NP D3P equal to C G of P, and just a change of variable, beta P squared by 2m. Now this is density of states. Let me first calculate this thing, what this is. So this is how many cells are there within this momentum range P and P plus dP, right? Or energy En E plus dE. How many states are there? So if you went through my previous lectures, then you remember in one class I talked about phase space and the volume in the phase space. So phase space is what? In just one dimensional case, you can have some x and px. Then there are of course x, y, z, then px, py, pz and all these things. So 6 x's, abstract mathematical. So I just wrote this x and px. So this is the simplest example of one-dimensional phase space, which becomes two-dimensional because of position and momentum. Now, you can take some minimum length for your convenience, dx, and some dpx, Classically, that can be as small as you want, right? In classical mechanics, infinite precision. You can go to like really zero size, and that will be okay. So that will be here. This will be your volume. In this case it's area, but imagine volume because we'll have other axes. So that's the volume of your phase space. And if we artificially partition them, such that these are just artificial cells, that will be considered equal, in a sense that anything that falls within, either in this box or that box, we don't consider that to be a different microstate. So remember, microstate is where the particles are, what are their velocities. One such snapshot is one microstate. Then you change them, it's another microstate. Okay, so once let's say the particle had a position this and momentum this, so this box corresponds to a microstate of a one-dimensional particle. If you choose here, so the particle had a different position and a different momentum, that will be another microstate for the particle. But if you choose the particle to be anywhere within this box, then you treat it like it's not a different microstate. Because within my dx, I consider this to be just this position. So if this is some x1, let's say, is the position of dx, then whether it's here or here is just x1. Because that's my minimum, precision. So within the dx, I don't differentiate. Okay? Similarly for the dpx. So that's why they are treated equally, these cells. Now these cells are again artificial. They can be as small as possible. But the thing is, quantum mechanically we know we cannot do that. There is a minimum precision set by the universe, set by the uncertainty principle. You cannot go beyond this. So if you choose, you have to choose some values that this is the minimum you can get. Usually very, casually we write that as h. So the size of the cell can be quantum mechanically will be minimum h, right? Will be minimum h. In case of 3 dimension, 1 dimension h, 3 dimension will be h cube. Will be the volume of this cell, the minimum cell. So how many cells are there? Obviously, the number of cells, let's call that G, okay, GP, DP. That is, what is the area of this whole thing? So that is dx, dpx, divided by what is the minimum size of this cell. So that is h. And that many cells will be there. So that's your GP, the number of cells or degenerate states within the smallest volume element in the phase space. So that's that. If you go to 3 dimension, so that will just become d3x d3p by h cube. d3x is dx dy dz, d3p is dpx dpy dpz. So that is just expanded. This is eventually we will move to quantum mechanics, and that's why from the beginning we are treating like there is a minimum. So here the density is this GP. I will look at this thing, p square. So eventually we'll have to integrate. I forgot to write d3p here. Another d3p will be here. Yeah. Once we integrate this, we'll be integrating the function of p square, right? The p square is the square of the magnitude of the momentum. So, which means it's rotationally symmetric because it is a scalar. There is no vector involved here, right? So, if it is a scalar and it's square, then whether you take it here or here, the direction doesn't make any difference. It's just a length. So p square is just a length, right? It's a scalar. So in that kind of situation, remember that you have a spherical symmetry. And it's easier if you switch to spherical polar coordinates instead of Cartesian coordinates, these d3p. Okay? And because there are no theta, phi involved, so it's even easier. You can just integrate out the theta phi. What will you get? 4 pi, right? In your volume element in spherical polar coordinate, you have some sine theta, d phi, r squared, dr, right? r dr and all these things. But then, just keeping the radius part, if you integrate out the angles, what do you get? The 4 pi, the total solid angle in 3 dimension. So 4 pi p square dp is the volume element if you don't have any theta involved. Here we do not have any thetas or phi's involved. So we'll just replace that. So gp dp, how much that will be? That will be just given by, of course, this formula. So you have d3x and d3 p divided by h cube. d3p really. Your d3x will be just here and d3p over h cube. So that you can write as 4 pi p square dp by h cube. Okay? 4 pi and the p square dp, this is your volume element in spherical polar coordinate. Where? In the p space, divided by, so this basically. So this thing becomes, this dxyz of course is here, separate. And this is just a 3-dimensional Cartesian written in spherical polar coordinates. So divided by h cube. So that's your gp d3p. Well, I can replace this then gp d3p by this. Right? So let me write that. Np d3p becomes c, then d3x, then 4 pi p squared dp over h cube, and then this exponential function. This will be just integrated to just total volume because nothing here depends on nothing here depends on position x. So it will be just total volume V. Then 4 pi p square dp h cube. Because when I asked how many states are between E and E plus dE, I meant in the whole volume. So keeping the momentum part, intact, because that is the range that you are giving. So try to understand this, that we're talking about energy range, so momentum range. But we mean in the whole volume. So the volume really gets integrated out. So your GP dP, that d3p is, this thing gets integrated out and this thing remains. So dpx, dpy, dpz over h cube. So that thing is just the total volume V. We didn't ask like how many states within the energy range E and E plus D and the range dx and dx plus dx and x plus dx, we did not. Only interested in the energy range and the position, of course, in the whole volume. In the whole volume. So you integrate the whole volume, and so that you get the this thing like this, and so just write it V. And e to the power minus beta p square over 2m. This is our final, so 4 pi v c, let me write all the constant in one part, h cube, and then this is here, p square e to the minus p square beta by 2m dp. That is our NP d3p. So what is this? This is the equilibrium distribution that maximizes your omega, maximizes your number of states. And this tells us how many gas particles are there in the momentum range P and P plus dP. Momentum magnitude range. Okay. So how many? This is how many particles are there in the range P and P plus dP. That's this. Next thing is we are going to find out what this C is. Remember? So to find out C, we can use the condition that when integrated NP d3p, we must get the total number of particles. So we can do that right now. 4 pi Vc h cube. Try to do the integration. So dp p square. Let me write this as just ap square for now. A is beta over 2m equal to n. This, of course, the standard integral for like this, or you can remember just one integral. So and that is what? If you remember this one, you can calculate the all other ones. So here we have a p square coming out. And remember a trick I told you. The trick was that if you know this integral, let's call this I. Let's call this I of A. Let's call this I of A, there is an A. And if you know this, you can calculate this integral, for example, dx x to the power 2 e to the power minus ax square. You can write this as, so let's call this some other integral, right? The one we want. So this is that integral. Let's call that I2. So I2 is this. We can write it as dx minus del A e to the minus ax square. Right? Of course, A is constant, we know. But for now, we forget about that it's a constant. Let's just use the value A, and A is not dependent on x. So we can take del A, so here x square minus x square will come down. Right? If you did this differentiation. And then what will happen? We'll get this thing. There is a minus. So we'll get that. So this means this. But then a does not depend on x, so we can pull it outside the integral, del a. Then all we have is this integration. And this is what? This integration, right? So this is minus del a of just I of a, or del a of square root of pi over a. Then in the end, whatever you have, put the value of a, this beta over 2m, and that will be a result of this integration. You can do this trick. So if you have x to the 4 here, what you do is take twice del square del a square, put it outside, you again have this integral, just you have to differentiate twice, and in the end put the value of a, right? So in general you can say in equal to 2n, I2n equal to 2n del 2n over 2n minus 1 to the power 2n. Let's just calculate this one, because this is the one we need right now. So that is minus just del a square root of pi over a, right? That will be just square root of pi and a to the power minus 3 by 2 and half. Oh, there is a half, by the way, and another half coming from this differentiation, half into a to the power half minus 1, so that becomes pi by 4, I think. Probably you don't remember this half because the integration was from minus infinity to plus infinity, but if it's from 0 to infinity, there is half. And why do we have 0 to infinity, not minus infinity to plus infinity? Think about the geometry. It's a radius. The radius starts from 0 and just increases. If it was Cartesian coordinates, then of course px can have minus px plus px. But when you go to spherical coordinates, it's just the radius, and radius has the minimum 0, and then it goes on up to infinity. Of course, infinity is nonsense because we said we are working with non-relativistic particles, and then then we are saying the momentum range goes to infinity. So it's a huge speed, right? So obviously we'll at some point go to relativistic case. When we start integrating, what is the integration? Basically sum of terms, right? Sum of terms. So initially fine, up to the speed of light, fine. And then you are started to take the p-values very, very high, those terms. And in those terms, it has to be relativistic. Otherwise, it will not make any sense. But fortunately, we are still safe and we can neglect relativity because of this guy sitting here. So this is e to the power minus ap square. E to the power minus something square is really fast dying object, and so this thing, you know, this thing looks like what? It looks like, so p square is like a parabola, and this thing is starting from 1 to dying out fast. So together when you multiply, you get a function that looks like this. Faster. Right? And that means even much before you go to the speed of light, this whole thing is 0. So the integrand is 0. So it's basically from 0 to some not so fast limit, and then other things are there, but they're like integrating 0, 0, 0, 0, 0, because this whole integrand has died out much before you go to the, you know, higher values of p. And that's why you can take this 0 to infinity pretty easily without any trouble and still say that no, we are all working in the non-relativistic case. You must know what is going on with every term, with everything. Nothing should, you know, fall from the sky. I might miss them, but you should ask. If not here, to yourself, like, no, I don't understand this. The easiest thing is to fool yourself when you read a book or anything. Yeah, I understood this. Yeah, this is like that. But really? Like, is it just fooling yourself? So the easiest way is to fool yourself. But don't fool yourself. Get stuck there. Don't leave that line until you really understand. Okay? But if you think like, okay, tomorrow I have an exam and I can't spend the whole night on this, okay, leave it for now. But come back after tomorrow and try to fix it. If you still don't understand, ask for help, but don't fool yourself. So, I mean, do this integral yourself. You know the answer. That's the answer. Just to verify that this is really half, I just wrote it from my memory. So, this is really half pi by a. And then you have a pi by 4 and a to the power minus 3 by 2. So, a is beta over 2m. Put it there. And then you have this integral. Write then c equal to everything on the other side. Find out what c is. V. Yeah, this will be your c. So do this as an exercise. Whatever I really do in the class, you have to repeat them yourself. Not watching the lecture or anything. Just try to derive them. And only then when you do that, you will understand. So you find out C and put it in the original value of this NP D3P. And then you have C gone. You are left with what? Just a beta. So what beta is, we'll do in the next class. But at least find out what C is. But if you really want to do it as a challenge, you know, if you want to do the beta as a challenge, then try that. Beta will come from the fact that total energy is E. I wrote down in the beginning, remember? E equal to integration of NEE dE. Energy term is there. So in terms of P, that will be integration of NP. E will be P square over 2M and then dP. And NP is all those terms, you know. So now you will have this P square plus another coming from E, P square. So you have to do an integration of P to the power 4, E to the power minus this thing, and that will be equal to your E. You can find out what is beta. Okay. It will be in terms of E. So find out beta, first of all C, and find out also beta in terms of E. I'll just give you this thing. NP and then E, dE, NEE dE will be your E. So just NE dE, of course, you write in terms of NP D3P. You know the value of this thing if you have noted down. It is 4 pi square P square E to the power minus blah blah blah. And this E is P square over 2M. Do this integration and the value of beta will come out in terms of E. Because remember, this is given. This is given, N is given, and V is given. So everything should be in terms of these things. So just do this integration. It will be P to the power 4 now, because a P square will come from this, and another P square here, and then do the integration using this trick. So now you have to do twice of this derivative of this thing, and that will be your answer. Some 5 by 2 here, some 3 by 2 factor.